Good morning, welcome back to the next lecture for energy conservation and waste heat recovery. Today we will try to wrap up and conclude our discussion on thermoelectric generators. Okay. You remember last time what we did was we tried to do some performance analysis of a thermoelectric module, and we came up with this expression where the efficiency of the thermoelectric generator was shown to be a function of a bunch of parameters. It was a function of the temperatures of the two junctions, that is TH and TC. It was a function of the properties which is aptly captured by this figure of merit Z, okay, which is Seebeck coefficient divided by the product of electrical resistances of the two junctions of the two elements, sorry, P and N, as well as the thermal conductances or electrical resistance as well as thermal conductances of the P and N junctions. Okay. It also depends on this parameter M, which if we recall is the resistance ratio. It is the ratio of the external load divided by the resistances of the P and N junctions. Clear? Also, if you look at it, this form is also quite nice because the first factor that we see here is the Carnot efficiency, right, as we saw, and then the rest of it is the other parameters, which is the combination of the resistances, the temperatures, as well as the material and geometric properties. So, we are going to depend on we are going to do further analysis on this. So, what does this depend on? What does, now if you look at it, what is it that we are going to that we can play around with? See, typically the heat source we cannot do much, that is available to us, we have to live with that. For example, if the heat source is steam at 150 degrees centigrade, my TH is 150 degrees, I cannot increase it any further. Okay. So, let us assume that TH and TC is something we do not have control over. The TC on the other hand will be mostly ambient temperature or an elevated ambient temperature, we really cannot bring it down further. Okay. So, what can we change? We can play around, if we look at this expression, we can play around with M over here, or we can play around with Z. So, let us do that and see what we get. So, I would say that eta TEG, that is, depends on 1 Z and 2 M, okay, which is again resistance ratio. Clear? So, let us take each of them one by one. First one is, as we can see, for Z dependence, it can be shown quite clearly that as Z goes up, my eta also goes up, plain and simple. Z increases, my efficiency increases. Now, what is Z again? Is alpha squared times R times K. So, what does this mean? That my Z max will depend on or will correspond to minimum value of R times K. Right. So, that is important. So, let us do that and see what happens. So, R times K is rho L, rho P LP over AP plus rho N Ln over An times the thermal conductances, which is Kp thermal conductivity times Ap over Lp plus Kn An over Ln. Clear? Okay. So, what I will do here is I am going to define a ratio of area to length, just so that it becomes easier to deal with this. I do not have to write it all the while. I will say that gamma of P is equal to AP over LP, gamma of n is AN over LN. Nothing spectacular, this is just to make lives simple here. So, then what this becomes is, this becomes rho p over gamma p plus rho n over gamma n times Kp gamma p plus Kn gamma n, fair and simple, right. So, now see, for a given material, rho p, rho and k are fixed. Okay. So, I can write here with a different color that rho p, rho n, Kp, Kn, these are all material properties. On the other hand, gamma p and gamma n are geometric properties. Okay. So, this I can play around, let us say I cannot play around with material, I can play around with these, okay, for a given set of material. So, what I will do is, I will do something like d of r times k divided by d of gamma n over gamma p. I will set this to 0, and this will imply that rho p k n is equal to rho n k p times gamma n gamma p to the power minus 2, or simplified further, gamma n over gamma p is going to be rho n k p divided by rho p k n. Okay. So, this implies that Z max corresponds to alpha p n divided by, becomes a very nice expression, rho p k p plus root over rho n k n, this whole thing whole squared. So, this is for a given set of materials. Okay. So, for a given set of materials, I can play around with the geometric parameters, and if I satisfy this equation, I choose the length and area such that this equation, this expression is satisfied, I get the Z max for that set of materials. Okay. Now, the other thing that I would like to point out, which is probably very important, probably the most important when we talk about any research on thermoelectrics, is R times K. So, this expression, let us look at this once again. If I just look at for a given dimension, so in the previous one what did we did? We assume the materials is given and we can play around with the dimensions. Now, let us say the dimensions are okay, fine, I can play around and I do this, but what else can I do to make this even higher? What are the kind of materials that we should have in order to maximize this performance of the thermoelectric? If you look at this, however, you see that there is an anomaly. You have three terms: alpha, you have thermal resistance and electrical conductance. Okay. So, what do I have to do? I have to maximize alpha, I have to minimize electrical resistance, but I have to minimize thermal conductance also. Okay. So, for high value of zeta or for high value of Z, my R needs to be low and my thermal conductance also needs to be low. So, in other words, I need a good electrical conductor and a poor thermal conductor. Now, unfortunately, the two of them, it is very difficult to satisfy both of them. Okay. It is not easy to have a very good electrical conductor which is simultaneously a poor thermal conductor, because most of them go hand in hand. Okay. For metals, for example, both are governed by the movement of electrons. So, how can you have a good electrical conductor and a bad thermal conductor? Similarly, in non-metals also, you have thermal conductivity, you have components because of electron movement, and you also have component because of lattice vibrations, which is also known as phonons. So, as a result, you know, for the almost last 60-70 years, scientists have been trying to, material scientists mostly, have been trying to come up with materials where we can maximize ZT, okay, or the value of Z. But unfortunately, for almost 50 years, from 1950s to early 2000s, it remained constant. Lots of you know, formulations, lots of new materials developed, but finally when you put it into practical use, we are all around the same value of ZT equals to 1. Okay. So, just keep in mind ZT, because it becomes non-dimensional, that value is often used. So, we were stuck at ZT equals to 1 for a long time for a given set of dimensions, and then what happened was, because of advances in nanotechnology, the almost two groups parallelly came up with a material which was again based on bismuth telluride super lattices. They were able to grow these lattices in the nanoscale and grow it in dimensions such that the electrons could pass through, because their mean free path of vibration is lower. So, it will let the electrons pass through, and therefore, electrical conductivity is not impacted, but however, it will arrest the movement of phonons and thereby impacting the thermal conductivity and arresting thermal conduction. Okay. So, this is just a side note from the research story I am telling you, that again what happened was, it is normally very difficult to have a material which is a poor thermal conductor and a good electrical conductor, but around 10 to 15 years back, two research groups parallelly came up with these super lattice structures at the nanoscale, such that what happened was, it would let electrons flow through, because electrons have lower mean free path of vibration, but it would arrest the movement of phonons, and thereby it would arrest the lattice vibrations, lattice movements, and thereby impact the thermal conductivity. So, as a result, we got materials which was a good conductor of electricity, but a very poor conductor of heat. And then as a result, what happens was, ZT value, which was stuck at 1 for a long time, at least in the lab scale, was shown to go to almost 2.5, both of them, a big jump. And this happened because we were able to grow these structures, at the nanoscale at dimensions which would arrest phonons and let electrons pass through. So, just a little side story on the research on materials part, which also helps us to increase or maximize the value of Z or Z. Okay. So, again coming back to what we were looking at, we tried to maximize the value of Z by playing around with the geometric parameters which is within our control, and we said that the maximum value of Z is this for a given set of materials, and this comes from satisfying this relation, gamma n over gamma p is square root of rho n k p over rho p k n. Okay. All right. What was the second thing that Z depend on? It depend on the value of m. So, eta will tend to eta max for an optimal value of m. Okay, m again let us recall RL over Rp plus Rn or RL over capital R. clear. So, let us do that. This will be a simple mathematical exercise. D eta dm equals to 0 will give us m optimum is equal to 1 plus z or z Tm, where Tm is actually the mean temperature Th plus Tc by 2. It can be shown. Okay, you can do it as an exercise. You take the value of the efficiency which we derived here and just differentiate with respect to m. Okay, all these are constants, and you will get this expression. Okay. So, what does that mean? This means that you do this, you square the two terms, etc., all that, and I would say that 1 plus m opt will be equal to z Tm divided by m opt minus 1. Okay. So, therefore, eta max turns out to be Th minus Tc over Th sorry, which is the Carnot efficiency, times, why did I do this? I did this to get something which is a very simple expression, okay, and this is that expression. This is eta max, and here let me write m opt 1 plus z Tm, and Tm is half of Th plus Tc. It is already defined here. Clear? So, this is how I can maximize the efficiency with respect to the resistance ratio m by choosing the external resistance such that the ratio satisfies this equation. So, the question may be asked is, I mean, can I do both? I tried to maximize the efficiency by maximizing the value of z, and I tried to maximize the efficiency by maximizing or by coming up with the optimal value of the resistance ratio, and the answer is yes. You know what we will do is, we will first play around with the geometry of the thermoelectric elements such that this z is optimized and we get that z max value, and then in order to play around with m and satisfy this relation, we will alter the external resistance value RL. Okay. So, we will only play around with RL, and that is how we are going to get this value of m optimum. Okay. So, it is possible. Clear? All right. So, this was for maximum efficiency, all right, but however, what we also need to do is, see, efficiency is definitely very important, because if I have an amount of thermal energy available to me, how much of it can I extract is definitely important, okay. But also equally important, probably depending on the application again, is what is the maximum work output, which may not correspond to maximum efficiency. That is okay. For a given set of elements and resistances and all that, what is the maximum work that I can get out? So, to do that, for maximum work output, what I will do is, I will go to this value of WL, which I recall is m into 1 plus m whole squared times alpha squared Th minus Tc whole squared, okay, alpha Pn, divided by Rp plus Rn. Okay. So, let me define this number by some constant, let us say equal to C. Again, just to all I am trying to do is simplify things a little bit. So, m 1 plus m whole squared times C. So, for WL max, what happens? dWL dm is equal to 0. So, which implies C into 1 plus m whole square minus 2 m 1 plus m equal to 0, which implies m is equal to 1, or R L is equal to R P plus R N. This gives you the maximum output, work output. Clear? What happens if it is lower than this, then R L value is low. So, I squared R L is going to be not the maximum value. If you have m greater than 1, and so which means the external resistance is greater than these, then what happens, the total current, the I value goes down, right, and therefore I squared R L again will not be necessarily be maximum. So, the I squared R L reaches a maximum point when this is satisfied. That may not be equal to the, or may not, or that is not necessarily maximum efficiency. Okay. So, therefore, let me write down W L max turns out to be 1/4 alpha squared P n T h minus T c whole squared divided by R P plus R n. Very important relation. And similarly, you can put this value into the definition of efficiency and get the corresponding efficiency as well, and as you will see that efficiency is not going to be the same as the eta max that we got in the previous exercise. Okay. All right. So, that is about the analysis. What we did was we did a lot of analysis on a thermoelectric module, and we got expressions for efficiency. Then we tried to see what does efficiency depend on and what all can we do within what is in our control to maximize either the efficiency or the work output, and we saw that the two are not necessarily the same. Actually, the maximum work output does not correspond to maximum efficiency. Okay. So, depending on what you want, if you want to have the maximum electrical output, if you have a lot of energy available to you and you want to have the maximum amount of work output, then you will go with this. On the other hand, if you want to use the energy very prudently, then maximum efficiency, we want to convert most of the output, that is most of the waste heat that is available to us and convert it to the useful electrical energy, then we will do something else, which was we will maximize the efficiency. Okay. So, what we are going to do next is we will wrap it up with a couple of configurations. How can we use the TEGs, the thermoelectric generators, in a combined cycle power plant, let us say. So, TEG in a combined cycle power plant can be used in two ways. These are just passing remarks. Okay. It can be used as a topping cycle in an ST plant, in a steam turbine plant, or as a bottoming cycle in a gas turbine plant. So, what it means is, in the first case, when I am using it as a topping cycle, then what happens is I am using the waste heat, or I am using the thermal energy source first as an input to the thermoelectric generator and generating electricity at a low efficiency probably, and then using the heat that is rejected, that QC that we saw in the previous analysis, using that as the heat input to the steam turbine plant. Okay. And as a bottoming cycle in the gas turbine plant is, we use the reject heat, the exhaust heat, or the heat contained in the exhaust gases from a gas turbine, and use it as a heat source for the steam turbine, use it as a heat source for the thermoelectric generation. Okay. Finally, what I will do is, I will end up with something called a cascading multi-stage operation. Okay. What that means is, if I have a large temperature difference available to me, what I can do is, I can utilize instead of using a single thermoelectric generator, what I will do is, I will have T1 and let us say I have T2 at the bottom, what I can do is I can have several TEGs. Okay. In this manner. So, what happens is there are intermediate temperatures that I am going to use. The first TEG operates between, let us say, the source TH and sorry T0 and let us say TH. I am sorry, let me write it down again, TH, and this is TC. Okay. And then I have T1, I have T2, I have T3, I have Tn and so on. Okay. So, then what happens is the efficiencies will be different. So, eta 1 is going to be 1 minus Q2 by Q1. So, I have Q1 coming in over here and then Q2 over here and so on, okay, which implies Q2 is going to be Q1 1 minus eta 1. Similarly, eta 2 is going to be 1 minus Q3 by Q2, which means Q3 is going to be Q1 into 1 minus eta 1 times 1 minus eta 2, and similarly we will keep on going, and finally what we will have is the eta overall is going to be 1 minus Qc over Q1, and this is going to be 1 minus eta 1, 1 minus eta 2 dot 1 minus eta n, or in other words 1 minus the product of I going from 1 to n, 1 minus eta I, right. And in case also which is equal to, or eta overall can be equal to 1 minus eta s to the power n if eta 1 equals to eta 2 equals to eta 3 eta n. Okay. Now, keep in mind, it does not always mean that if you keep increasing n, my overall efficiency increases. It comes, this actually this expression gives you that impression that if you keep on increasing the number of cycles in the number of stages, my overall efficiency will go up. But that is not the case, because every time what happens is, where as you increase the number of stages, I am reducing the temperature drop across each of these thermoelectric generators. So, therefore, my eta s, so the individual efficiencies of each of these thermoelectric generators will keep going down. Okay. All right. So, what it means is, if I keep on increasing n, my eta s will also change or rather reduce. So, therefore, it does not necessarily mean that if I keep on increasing indefinitely the number of stages, I will keep on increasing, I will keep on getting higher and higher efficiencies. All right. So, it is limited by the temperature band. All right. So, that kind of brings us to the end of thermoelectric generation, and we have studied a lot of things. We started with understanding what thermoelectric generation is, what are its potential applications, where it is used today for waste heat recovery, and then what we did was we went into the analysis of the thermoelectric module, trying to see what is the how do we calculate efficiency, how do we do energy balance, and then how do we maximize the efficiency, and what all does efficiency depend on. And finally, we wrapped up by a small discussion on cascading multi-stage operation, where for a given temperature difference we can use several thermoelectric generators in stages, and how do we calculate efficiencies for that. Okay. So, that was the first type of direct conversion device, which directly converts thermal energy to electrical energy using solid state device, no moving parts, no working fluids, and I hope you learned something new through this discussion. And what we will do is, in the next lecture we are going to move on to another type of direct conversion device. Okay. Till then, thank you very much.